Welcome back. So we're going to take a break from electricity, and we're going to start to talk about a new phenomenon that's known as magnetism. Now, if you'll remember, when we first started talking about electricity, we developed a mathematical model to describe this interesting phenomenon where I saw things attract and repel each other. But much of the mathematics behind that model was actually derived from what we knew about from gravity, right? So things like the 1 over r squared dependence and being able to set up potentials and all of that were things that we had learned when we talked about gravity. And the thought process here went, well, I have a different kind of charge, which we call electric charge as opposed to mass. That charge led us to electric fields. Those electric fields give us forces. And then I'm able to write down really compact expressions, even in vector form, that allow me to calculate those electric fields based on the charges involved. But more importantly, it also gave us interesting mathematical relationships like Gauss's law, right, that said that the electric field over some surface is equal to the charge enclosed divided by some constant, right? That this integral of the electric field over a surface was proportional to the charge inside. I was able to get neat mathematical relationships that turned out to be really useful. Well, hopefully all of that work that we had for electricity will come in handy if I see some new phenomenon where, say, I have some new charge q prime. Maybe I'll be able to write down some new field, right? So this isn't electricity, but some other kind of field that leads to some new forces, right? Maybe all of the work that I did for electricity will pay off, and I'll be able to calculate these new fields. Maybe they'll have some different constants. I'll just throw it as mu instead of an epsilon, where, again, the field is going to be proportional to 1 over r squared. And then maybe because this mathematics is the same, because the model is the same, I'll be able to do things like calculate the integral of this new field over some surface, and it's going to be proportional to the charge that's enclosed. Okay, well, this is the hope, right? This is the sort of hope with everything that we do, that all of the work that we put into developing one mathematical model might be valid in some other regime. So, picture it. You're walking through the land of Magnesia when you come across two rocks, and lo and behold, when you pick them up, they stick to each other. But that's not enough, right? Because in order for it to look like electricity, something has to be a little bit different. So imagine you take one of the rocks and you flip it upside down, okay, but you keep the other rock the same way. Well, you do this experiment, and what happens is the two rocks tend to repel each other. And now you have a situation in which you have things that attract in one regime and things that repel in another regime, and you say to yourself, well, excellent, right? This reminds me so much of what I was doing with electricity that maybe I can take some of what I know about electricity and model it after this problem. So you say, okay, well, let me take this one rock and let me try to apply what we used to know as Gauss's law to this rock. So I'm going to say that whatever phenomenon here now creates these new fields, which we call B. Because I was in Magnesia, I will call it magnetism, and therefore this B is going to be the magnetic field. This mu naught is going to be the magnetic constant, and the thing that I'm looking for, Q prime, is then the magnetic charge. And so with the phenomena that I saw, I know that I can explain all of this if the rocks themselves represent the field that corresponds to a dipole, right? So if I had two electric dipoles, and I had them anti-aligned, they would stick together. If I had them aligned, they would repel each other, and so all of the phenomena there works out. And so the only thing that I have left to do now is take this model, this mathematical model, and try to apply it to the rock by taking Gaussian surfaces and identifying where the new charge is. So if you take a Gaussian surface around the entire rock, well, if it's a dipole, I expect the charge enclosed to be 0, and in fact, when you integrate this field around the entire rock, you do get that the charge enclosed is 0. Of course, in order to keep going with this, I have to take now a Gaussian surface that's only half of the rock, with a hope of finding out how much charge there is here, right? This will actually help me to measure mu naught or something. So I take the integral now, the closed integral over this Gaussian surface of B dot dA. I hope to get the charge that's enclosed in the top part, but I get 0. Okay, well, maybe it's two dipoles. So I take another Gaussian surface here, and I take the integral of B dot dA, and I get 0. So I take another, well, okay, I take a Gaussian surface here, and I take the integral of B dot dA, and I get 0. No matter how I slice up this rock, it turns out that the integral of B dot dA is always going to be 0. There doesn't seem to be any charge at all inside this rock, right? I have the phenomenology associated with the dipole, but I have no monopoles. I have no charges that I could use in order to break down this rock into the pieces that I was hoping to see. And because I have no charges, but I seem to have attraction and repulsion, that actually causes me to completely abandon everything that I did with electricity in order to model this phenomena. If I don't have charges, I can't write down fields as a function of those charges, right? So I'm stuck now with having a new phenomena that I was hoping was going to remind me of electricity, but for the time being has no charges whatsoever, and therefore I have to deal with the fact that there's no way to model this phenomenology in the same way that I did with electricity. So you go back to the drawing board and you take objects and you put it near these rocks, and eventually you find out that you can write down a mathematical description for what the forces look like. And the mathematical description says that the force that you see on one of these rocks is actually equal to the cross product between the velocity and the magnetic field. Okay? And then the constant of proportionality between the force and the cross product between the velocity and the magnetic field is the amount of electric charge that the thing that you're studying has. Okay? So my force is proportional to the magnetic field. It's proportional to how much electric charge it has, but it cares about where it's going. And so what you're left with is an expression that allows you to calculate forces due to the fields that are generated by these rocks. But it's something that so far we've only been able to determine empirically. Now, there are three observations of this law, right? That the force is proportional to the charge times the cross product of the velocity with the magnetic field. One, this is going to be a lot harder, right? I'm not able to do, I have a cross product in here. I'm not able to talk about the force being proportional to the field. All of my intuition about what field lines really mean in this regime are no longer there, right? This is a mathematical structure that's a lot more complicated than the mathematical structures we saw for electricity. We also see that the force being proportional to the cross product of V and B means that it's perpendicular to both of the two vectors that are important to the problem, right? So the force is perpendicular to the velocity and it's perpendicular to the magnetic field. And because of that, because the force is perpendicular to the magnetic field and perpendicular to the velocity, that means I have three directions in my problem all the time. And so the most difficult thing about magnetism, and it's something that we have to accept from the beginning, is that magnetism is inherently and necessarily and 100% and all the time a three-dimensional phenomenon. Okay? We have to worry about the fact that there are three dimensions. We can't write vectors just in terms of two components. We can't reduce it to just what's going on in the plane. We have to talk about magnetism in a three-dimensional way. So your take-home messages are this. Magnetism is not the same as electricity, at least not for now. And it's really hard. Well, okay, it's harder than electricity is, right? Because we have to worry about all of the things that I mentioned on the last page, that it's three-dimensional and that it has this cross product. But we do see already a connection between electricity and magnetism because the constant of proportionality that defines the strength of the magnetic force is proportional to the electric charge.